Okay, everybody. We're going to keep going with the standard operating procedure. So now we're getting to the portion talking about selecting archetypes and template models. Now, again, this is very controversial. If you ask different people whether they use previous models or not, you will get very different answers. I just find that using archetypes and template models actually help the novice modeler just to start with something, at least to at the minimum to have some ideas in terms of how to model the phenomenon. So what we're going to do now is to explore three different sources from which you can get either an idea or some initial structure to model your model. So just going back, what we mentioned before is that we were looking at a model where we basically had mice. We had mice that were growing with unrestricted food, but in limited space. Now, this is the typical condition for a cage, right? So, you provide as much food as, the mice want, but, they can only grow so much because, there's limited space. What we know from biology is that as the situation starts getting crowded, their rate of reproduction goes down. Okay, so where can we find a model, an example that would be something like this? Well, the first step or the first source that the SOP mentions is this archetype. So let's take a look at what that means. Basically, the archetypes are a standard way of thinking about some of the most common structures in system dynamics that cause a given type of behavior. So again, you could go over here. There's a number of different uh, previous archetypes. I'm just going to jump through. Well, there's accidental adversaries, balancing loop, drifting goals. But basically, I'm going to tell you that, already knowing this, maybe at some other point, we're just going to go over all the different archetypes and their corresponding behavior patterns. But for this example, basically, we're going to be looking at something called a balancing loop archetype. So in the description, it says that attempts to move some current state of a desired or reference to some action. Basically, it has a balance, okay? So as a balance, it basically does the following. It starts growing, and it seems like, it's never going to stop to grow, but then it reaches a balance, and then it stops growing. It reaches a plateau. It basically has three phases, if you will. A first phase of a slow growth, then an accelerated growth, and then a plateau. And this is kind of, what we're looking for, if we're thinking in terms of mice. So basically in this phase, you only have a few mice. So, the number of mice is, this is time, and this is the number of mice. So in the beginning, they're growing slowly, because there's not a lot of them. Then they grew really fast. And then at this point, or maybe somewhere around here, but here more pronouncedly, um, the space restriction starts kicking in. And then they no longer grow in terms of numbers. Their number of mice actually remains stable. Uh, because they don't have any more space to grow. So basically this archetype would give you an idea of what it takes in terms of structure to build something like this. So you have to have a balancing loop, which means that there is a I was clicking on the wrong button. Now it's not gonna show up again. So took me two videos to figure this out. That's okay. So basically, you know you have a negative influence and this is basically this is going to come from what we call the desired state. So this variable here, desired state, later we're going to see, it's basically a way of restricting the growth of the mice based on an assumption on the relationship between number of mice and space. Okay, but we're gonna see this in detail later on. So this basically would be the first way of trying to find previous examples. The second possibility is to use what we call molecules. Now the molecules, there's a story and actually a very good paper about the molecules. But the molecules was a collection of patterns, structural patterns, put together by an outstanding system dynamics modeler called Jim Hines. So Jim has put together this collection of models. I'm going to show you what that looks like here. I have already preloaded this just so that you can see. Let's try to make this a little bigger. Well, I don't know if it's going to be too easy to see this, but there's a number of different models here. Okay, so basically, this makes use of what Vincent calls views. So every time you click on a different model, you end up getting the structure for that model. So this is very handy. So Jim Hines did a lot of work to put this together. He consulted a lot of different papers and books, and this is an amazing resource. So basically what you can do is you click on one of these, grab the model, and then transport to your model. So this is another very good way of actually finding pre-existing models. Now, let's get rid of this. And then the third way is actually to find previous models. Now, the way of finding previous models that I find most useful is to go to the System Dynamics download page for their references and then downloading either their text files or their EndNote file. Now, what you have here is an extremely good and large database with all sorts of previous papers using System Dynamics, and then you can search by title, you can search by text, and look for the paper that's the most appropriate for you. Okay. Now, what I have done is that I have used a model. Yes. Oops. Just open Vincent again. But instead of going through the library, what I have done is that I have cheated. And I have used a model that's already available within Vincent. And this is basically the model that Vincent has is preloaded. So basically, as you can see here, there's a stock, which is mice. Um, there is a limiting factor here, which is the effect of the density on survival. And this is basically what provides the negative feedback. So if you look at this balance here, this is the negative feedback or the balance. So basically it's a negative because, as the number of mice increase, after a certain point, later on we're going to see this, the number of mice starts decreasing. How do I know this? Well, basically if I click on the effect of, just do that again. If you look at that variable, here, let me just put it down here for a sec, on the effect of density on survival function, and basically what I did was to click on the equation button, and then click on the effect of density. If I come here and I click as a graph, it basically shows me that, um, as I start increasing the input, which is the x variable, so the x variable is recorded in this x axis. Uh, so you start with 0 mice, and then you start going up and up and up. So you go from 0 to 4. So here's 0, and here's 4. Then the number of the potential growth of the mice starts decreasing. So the output, which is the growth factor, will go from 3 all the way down to 0. Okay. Now, this is the balancing loop. And then there's another loop here, which is mice create new mice, which then, adds to the pool of mice. Now, as you can see here, this little thing here, it took me a while to figure this out in system dynamics. But basically, this means a snowball. So this is a balance, and this is a snowball. Now, what the snowball says is that, there's a positive feedback. Of course, if you have like mice, they reproduce and generate new mice, and then it adds to the pool of mice. So basically, what you have here is a positive feedback and a negative feedback, and this will actually explain why you have this growth. So just get that back. Try to put the two side by side. So basically, in this stage here, all the way up to say here, uh, the the number of mice is actually increasing, right? So this is where the positive feedback is kicking in this entire portion of the model. But then, once it reaches a certain number of mice, that graphic that I showed you starts kicking in, and basically from here on, the negative feedback starts, kicking in. And then, you understand why this is called a balance, primarily because it balances the growth of mice. Okay? So basically, we went through, the three possible sources of previous models for your model. Uh, the principles are always start with a simple structure and then add complexity. So for a model like this, you might, for example, assume that their food is going to run out, or something else is going to happen. But start with a fairly simple model. And number three, keep the model endogenous. Basically, what that means is simply that and this is a widespread belief in system dynamics, that usually the components within the system will explain the growth or the behavior of the model. So for example, when I run this model, so basically I just ran this by clicking on the little guy here. Then I click on this variable, and I click on the graphic, and it generates a graphic for me, which is exactly what I expected, right? So in the beginning, a little growth, then it grows fast, and then it reaches a plateau. Basically, the endogeneity here comes from this behavior that I have hypothesized can be explained just by oops, these variables, right? I don't need anything else. I don't need like sun, or I don't need like the researcher observing the mice or anything like that. So basically, this is what we had for now. Next time, we're going to get into model validation.